So in this video, you're going to have a go at a few of the questions in your pack, and then we'll have a talk through the answers. So what I want you to do is pause your video and have a go at these questions, and then we'll go through and explain. So pause the video now and have a go at this page. So let's have a look at the first question. It says chlorine gas is bubbled into a mixture. So the first thing we need to do is identify something's chlorine gas, that's here, is bubbled into a mixture of these two, iron 2 and iron 3. What will you see happening? So the first thing you have to identify is which one gets to go the way it's written. So the most positive one, which in this case is the chlorine one, is going to go the way it's written, forwards. But the more negative one is going to go backwards. So what we can say is chlorine is going to cause the oxidation of Fe2+. And then we can combine our two equations, making sure we double up if needs be. So we've doubled the Fe to make the electrons the same. So our top one went forwards because it was most positive, and the iron one went backwards because it was more negative. So have a go at part B. So if we look at this second example, hydrogen gas is bubbled into a mixture of iron 2 and iron 3. So let's go back up. Hydrogen gas is here. Oops, that was the wrong highlighting colour. Let's just correct that. So hydrogen gas is here, and our iron 2 and iron 3 are here. Remember that the most positive one gets to go the way it's written as reduction. The hydrogen gas goes backwards. So this time hydrogen is being oxidised and iron 3+ is being reduced. So we ended up with a different answer. So just because you bubble a gas into a mixture of iron 2 and iron 3 doesn't mean you'll get the same product. It depends what that gas is and whether it's more or less able to reduce or oxidise than the iron 2, iron 3. Right, so here's a typical exam question on this topic. So they print you out a section of the electrochemical series, they show you that, and they ask you to write something down. So write the conventional representation for, and it's asking us to do it for 2 and 4, so 2 and 4. Right, so first thing I would do is decide who's on the right hand side. Most positive on the right hand side. So this is going to be my right hand side, and this will be my left hand side. So I'm going to draw my salt bridge in, and I'm going to put the most positive on the right hand side with the highest oxidation state nearest the salt bridge. So out of 3+ and 2+, I'm going to have Fe3+ first, and then I'm going to have Fe2+. Are these two things in the same phase? So they're both AQ, so they don't get a line, they just get a comma. Can I connect a crocodile clip to Fe2+? Nope, so I need to put a platinum electrode, which is a solid, so there's a phase boundary. Then I'm looking at cell 4, it's going to be my left hand side. Out of 2+ and Cu, 2+ is the highest oxidation state, Cu is the lower. They're different phases, so there's a line, and I can connect a crocodile clip to Cu. So I stop at that point. Okay, state. When a question starts with the word state, you're supposed to just know the answer. You don't need to be working something out. So what goes? Charge carriers are things that carry current. So right back in the bonding pack, what flows through wires? Wires are made of metal. How do metals conduct? And what flows through the solution? The solutions are ionic. What makes ionic solutions conduct? So electrons make wires conduct, and ions make solutions conduct. And then we have to write an overall equation for cell 2 and 4 together. So remember that the one on the right hand side gets to go forward the way it's written, and the one on the left hand side gets to go backwards. And we need to make the electrons match. So at the moment we would need to double all of this top one in order to make them both have 2 electrons, and then we need to combine those, remembering that that bottom one's got to go backwards. So you need to be careful. You're starting with copper metal, because you're doing the bottom one backwards, I'm going to do that bit first so that I don't fall into the trap of doing them the wrong way around. And then I'm doing the top one forwards. We've got 2 Fe3 pluses becoming 2 Fe2 pluses. And a double check to make sure you haven't gone wrong is to add up the charges on each side. So 0 for the copper, and 2 times 3 is 6. Then go to the right hand side, 2 and 2 times 2 is 4. That makes 6 as well. So 6 on each side. Calculate the EMF, which is right hand side minus left hand side. So plus 0.77 minus the left hand side, which is plus 0.34. And we get 0.43 volts. Right, now we're moving on to the slightly more difficult parts of the question. So a species, something, so they're not telling us whether it's an element or an ion, it's just something that could oxidise Fe2 plus to Fe3 plus. Let's go back up. Let's just get rid of all this annotating that's getting in the way now. We want Fe3 plus to turn into we want Fe2 plus even to turn into Fe3 plus. So we want that one to go that way. We want Fe2 plus to turn into Fe3 plus. So for that to go backwards, we need to find something with a more positive value to go forwards. So this is 0.77, and they've not put this in order to confuse us. Well, that's not more positive, that's not more positive, that's not, and that's not, but these two are. And if this one has got to go backwards, these two would go forward, so it would either be this or acidified oxygen. Okay, so what could cause, the oxidising agents, remember, are on the left. So what could oxidise? So Cl2 is what I would pick, because if you pick the oxygen, you have to write oxygen / acid. And for our last one, a species which could reduce Fe3 plus to Fe2 plus, but does not reduce Cu2 plus to Cu. What that means, it's going to have to fall in between these two in the table. So we'll cause that to go forward, but we'll not let this one go forward. So if this is going to go forward, the top one, then our other cell needs to have a number lower than 0.77. But if it's going to stop this one going forwards, it needs to have a number higher than 0.34. And the only thing available to us is this bottom one here. And if we're going to cause reduction, we need to be a reducing agent, so we need to be the thing on the right. So it's very important that it's not iodine, it's iodide. So it's the one in between the two things we're being asked about. So in your pack there are 2 more questions, but you can look the answers up to these on the virtual learning environment, or speak to your teacher about them. They're just repeating the same sort of skills. So if you're not sure, get in touch with your teacher and ask them how you would solve these problems.